Imagine looking up on a clear night, far from city lights. You see the Milky Way, a river of stars. But in the southern hemisphere, you might spot two faint, hazy clouds, the Magellanic Clouds. These are our closest galactic neighbors, visible to the naked eye for millennia. The large and small Magellanic Clouds orbit the Milky Way in a slow, cosmic dance. They have fewer heavy elements than our galaxy, making them windows into the universe's past. By observing them, we ask, how do stars form with fewer raw materials? The Magellanic Clouds are more than companions in the sky. They're clues to our cosmic origins. And now, with new technology, we're finally able to unlock their secrets. To unlock the secrets of these distant galaxies, we needed a new kind of eye, the James Webb Space Telescope, or JWST. Launched in 2021, JWST orbits 1 million miles from Earth with a massive gold-coated mirror to collect faint light. Its real superpower? Seeing in infrared, light invisible to us, but crucial for peering through cosmic dust and seeing the earliest galaxies. Infrared lets JWST look back over 13.5 billion years and peer into stellar nurseries hidden from view. To do this, JWST must stay colder than any freezer on Earth, protected by a tennis court-sized sunshield. Its mid-infrared instrument, MIRI, is a master at reading the chemical fingerprints of molecules across the universe. By splitting faint starlight into its component wavelengths, MIRI reveals exactly what molecules are present, even across vast distances. This extraordinary power led to a discovery that changed everything. With JWST, we can now study the chemistry of galaxies far beyond our own. And what it found in the Magellanic Clouds was astonishing. In 2025, Dr. Marta Sawilo's team used JWST to study a stellar nursery in the Large Magellanic Cloud. They focused on a young protostar, ST6, still wrapped in a cold cocoon of gas and dust. Around ST6, a swirling disk of material, future planets in the making, was coated with thin layers of cosmic ice. These icy grains are chemical factories, where simple atoms combine into more complex molecules. Using MIRI, the team captured the faint infrared light from ST6, which had traveled 160,000 years to reach us. The light carried the chemical fingerprints of the molecules in the ice. The data was stunning, more detailed than anything seen before, even in our own galaxy. They found not just simple ices, but a suite of complex organic molecules, the building blocks of life. Discovering them in another galaxy, with a different chemical environment, was a revelation. It sent ripples through the scientific community. The discovery at ST6 wasn't just a hint, it was a detailed inventory. JWST identified 5 distinct complex organic molecules, or COMs, in the ice. These included methanol, ethanol, methyl formate, acetaldehyde, and acetic acid, molecules familiar from everyday life. Finding them frozen in ice is crucial. It protects them from destruction and allows them to be incorporated into comets, asteroids, and planets. This was the first time ethanol, methyl formate, and acetaldehyde were detected in ices outside our galaxy. Even more remarkable, it was the first ever conclusive detection of acetic acid in interstellar ice anywhere. JWST's sensitivity made this possible. There was even a tantalizing hint of glycolaldehyde, a simple sugar-related molecule, vital for forming RNA. While not yet confirmed, its possible presence is profoundly exciting. The cosmic recipe for life might be more universal than we ever imagined. The universe, it seems, is using the same ingredients everywhere. Let's zoom in on methanol and ethanol, 2 alcohols found in ST6's icy disk. Ethanol is the alcohol in beer and wine, but here it forms in space as atoms stick to dust grains and build up over time. Methanol, the simplest alcohol, is a cornerstone of interstellar chemistry and a stepping stone to more complex molecules. Finding both in the LMC shows that even in metal-poor environments, complex chemistry thrives. The leap from methanol, 1 carbon, to ethanol, 2 carbons, is a big step in molecular complexity. It's like going from building a wall to constructing a house with Lego bricks. These alcohols prove that the universe can manufacture complex organics in the cold, dark spaces between stars. Delivered by comets and asteroids, they could seed young planets with the ingredients for life. The presence of these molecules in another galaxy tells us the chemistry that leads to life is not unique to the Milky Way. The universe is busy mixing its own cosmic cocktails everywhere. The ingredients for life's recipe are more common than we thought. And that changes everything. The most stunning find was acetic acid, the molecule that gives vinegar its tang, detected for the first time in interstellar ice. Acetic acid is closely related to glycine, the simplest amino acid, a building block of proteins. Its presence suggests that the pathway to forming life's essential molecules is common, even in harsh environments. The other molecules, acetaldehyde and methylformat, add more branches to this chemical tree. They show that cosmic chemistry isn't just about simple chains, but a rich diversity of structures. For life to begin, you need a varied chemical environment, not just 1 or 2 molecules. The discovery of 5, possibly 6, complex organics at ST6 proves such environments exist even in metal-poor galaxies. The LMC isn't a barren wasteland. It's a vibrant chemical laboratory. It's busy cooking up the organic soup that could one day seed new planets. The universe is more chemically creative than we ever imagined. For years, we found complex organics in our own Milky Way, but wondered, is our galaxy special? The discovery in the Large Magellanic Cloud answers that. No, the Milky Way isn't unique. The processes that create life's building blocks are robust and widespread, even in galaxies with fewer heavy elements. This is a scientific milestone proof that the raw materials for life are a common byproduct of star and planet formation. Wherever stars are born, the potential for life's ingredients is born with them. Now, every faint galaxy in deep space images could be a crucible of cosmic chemistry. The building blocks of life are not just local, they're galactic, maybe even universal. This realization expands the possible locations for life by an unimaginable degree. The universe is not a barren desert, but a landscape dotted with oases of chemistry. The odds for life elsewhere just got a lot better. The Large Magellanic Cloud is a portal to the past, a model for early galaxies with fewer heavy elements. Scientists wondered if such metal-poor galaxies could form the complex molecules needed for life. The discovery at ST6 turns that idea on its head. Even in a galaxy with limited heavy elements, the chemistry for life's building blocks is active. This means the universe was ready for life much earlier than we thought. Habitable planets could have formed billions of years before Earth. If life can start earlier, it has more time to evolve. The universe might be ancient, filled with the history of life. We may be latecomers to a cosmic story that's been unfolding for eons. The search for life just got a lot more interesting. The discovery in the Large Magellanic Cloud is just the beginning. Is ST6 unique, or is this chemistry common? Scientists are already expanding their search with JWST. We now know that complex organic molecules, the starter kit for life, are widespread and ancient. These molecules, delivered to planets by comets and asteroids, could spark biology across the cosmos. We haven't found life, but we found that the ingredients are everywhere. The universe is hardwired for complexity, forging the building blocks of life from the simplest elements. Are we alone? We still don't know, but the odds have shifted. The same recipe that may have cooked up life on Earth is at work in other galaxies. As JWST continues its mission, we're closer than ever to answering humanity's oldest question. The universe is looking less empty and more like home.